Welcome to problem 14, Inductor Current, Power, and Energy. Okay, so for this problem, it states that if the voltage across a 200 millihenry inductor is given by Vt is equal to 1 minus 3t e to the power of negative 3t millivolts, what is the current, power, and energy? So we're going to separate this problem into three. We're going to solve it for current. So the current going through an inductor is given by 1 over the inductance, the integral from 0 to t Vx dx, where Vx is just the voltage given in the variable x. Okay, so from there what we could do is we could integrate. We could substitute L for 200 millihenries, which is just 200 times 10 to the negative 3. The integral from 0 to t, and then we have the Vx dx voltage. So if we do that, what we could do is we could distribute e to the 3x into this bracket over here, where we get e to the 3x minus 3x e to the 3x dx. What we could do from here is we could say, okay, well, it's a linear formula. So what we could do is we could actually separate this into two integrals, where we have one integral, e to the 3x dx, and the other integral, negative 3x e to the 3x dx. Okay, so let's solve for the first integral. Solving for the first integral on its own, from integral from 0 to t e to the 3x dx, what we know about solving for exponential integrals is that it's equal to 1 over a e to the ax, where we could see over here. So we could see that a is just negative 3, and it's just a simple integral where we end up with e to the 3x divided by negative 3, 0 to t. When we have an integral like this, we put in t first, and we put in 0, and we subtract them from one another. So for example, we put in the first upper bound, and then we subtract the second lower bound. So like this. So we have e to the 3t divided by negative 3 minus e to the 3 to the times 0 divided by negative 3. E to the negative 3 times 0 is just equal to 1. So this becomes 1 over negative 3. Since there's a negative sign over here, it becomes positive 1 over 3. Okay, so we solved for the first integral. Let's solve the second integral. The second integral is 0 to t minus 3x e to the negative 3x dx. So we could see that there's two variables. We have an x and we have e to the negative 3x. To solve an integrand like this, what we could do is we could do integration by parts. Integration by parts is fairly simple. We have the integral of u dv is equal to uv minus the integral of v du. So what we could do is we could take the integral of e to the negative 3x. The integral of e to the negative 3x, what we did was the first integral, is just e to the negative 3x divided by negative 3, which is this. And we have x as well. We subtract the integral from 0 to t, and then we take the derivative, which is du, which is the x value. The derivative of x is just 1, and we have this integral here. So we have the lower bound 0 to t, where it goes from negative 3 times 1 e to the negative 3x divided by negative 3 dx. Now we can eliminate negative 3 here and negative 3 here, and 1 times e to the negative 3x is just e to the 3x. So simplifying and taking the integral of this, what we could do is we could find the integrand from the lower to upper bounds. So putting t where the x is and subtracting where 0 where the x is as well. So when we do that, we end up simplifying it even more actually, because the negative signs cancel out and become positive, and we end up with an integrand, the final integrand like this, where it's t e to the negative 3t e to the negative 3t divided by 3 minus, and then we put in zeros for the x's, 0 times e to the negative 3 0, 0 times any number is 0, plus e to the negative 3 0, this is 1 over 3. You can see here. Simplifying further, we distribute the negative sign, and we end up with the final formula like this. Okay, so now we solve for two integrals, and we could sub it into the original equation. So we solve for this integral, and we solve for this integral. So let's put it all together, and we end up with an integrand like this. As we can see, these terms, this one and this one, cancel out, and this one, 1 over 3, and negative 1 over 3 cancel out. And we're just left with t e to the negative 3t. To simplify even further, 1 over 200 times 10 to the negative 3 is just equal to 5. So we have 5t e to the negative 3t milliamps. And that is the final equation for the current going through the inductor. Okay, so now let's solve for power. Power is just Vt times It. So we were given Vt and we solved for It. So we could just sub them in together and take the product. So when we sub in Vt, we have this equation. When we sub in It, we have this equation which we just calculated. And what we could do is we could see how there's an e to the negative 3t and e to the negative 3t here. Exponent rules state that this is just minus 3 minus 3, which is negative 6t. Then we bring the 5t over to the front, and we could distribute into the brackets, and we end up with 5t e to the negative 6t minus 15t squared e to the negative 6t microwatts. Micro is just 10 to the negative 6 because we have the voltage in millivolts and we have the current in milliamps. Okay, so now let's solve for energy. Energy is given in the formula of 1/2 times the inductance times IT squared. So we solve for IT, so we could plug that into the equation, and we have 1/2 times 200 times 10 to the negative 3 times 5t e to the negative 3t squared. Squaring it, we could simplify it. So 5 squared is 25, t squared, e to the negative 6t. Remember, negative 3 minus 3 is negative 6. And what we could do is we could simplify that even further, and we end up with 2.5 t squared e to the negative 6t microjoules. Alright, so we solve for current, we solve for power, and we solve for energy of an inductor. Awesome. Thank you for viewing the video.